Welcome to AC's Simplified Lectures for Electrical Engineering subjects. Our topic for today is the basic principles of AC circuits or alternating current circuits. So, when we talk about the alternating current circuits, so alternating, so we're going to talk about sinusoidal wave function. So, let's say you're given a sinusoidal wave function as shown. So, let's say a function yt am sin omega t. So, where your am is your amplitude or the max value or maximum value, your omega is the angular velocity, which is omega, which is 2 pi times the frequency, and t is your time, small t. So, this one. So, what is this capital T? This capital T is your period in seconds. So, what is the period? Period is the time it takes for one cycle, one whole cycle to complete. It takes the time it takes one complete cycle. So, what is the frequency? The frequency of the sinusoidal wave is the number of cycles done per second. So, this is equal to 1 over the period. So, for the wavelength, this is the length of one cycle. This is in terms of either meters, centimeters, etc. So, this is in terms of lambda. Lambda is equal to Vc over F, or in which Vc is equal to 3 times 10 to the 8 meters per second. This Vc is your speed of light, so or speed of radio waves. So the RMS value or effective value of alternating current. So take note that for AC circuits, your source or your supply is a sinusoidal wave function. So for your RMS value or the effective value of your sinusoidal wave, this is equivalent to the DC. This RMS value is the value in which your energy consumption or your energy usage for this wave is equal to the DC. So this is the RMS. So RMS is equal to AM over square root of 2, in which AM is equal to in which AM can be the maximum current or the maximum voltage. So for your average value, this is equal to 0.636 AM. You take note that these two formulas is just applicable for one whole sinusoidal wave. So this is not applicable to other form of functions. So take note also that this average value is equal to the mean of all the instantaneous values in a half wave or half sinusoidal wave. So what is instantaneous value? So the instantaneous value is the value of a certain function at a certain time t. So next one is the form factor. So form factor is the ratio of your RMS to average value. So RMS over the average. The peak factor is equal to the ratio of your maximum to the RMS value. So the peak value is your maximum value. So yan, over the RMS. So number 2, if we talk also about when we talk about AC, we're going to talk about reactance and impedance. So what are these two things? So reactance is the property of the inductor and capacitor to oppose electric current. So as we talk about as we have discussed before, we have the resistance. This is the property of any material to oppose the flow of current of the DC current. So, for this is the property of inductor and capacitor. So, XL, so the reactance of the inductor, XL, is just equal to omega L. So, this is also equal to 2 pi FL, where your L is the inductance. For the reactance of the capacitor, this is this is called capacitive reactance. This one is the inductive reactance. So, this is equal to 1 over omega C. So, this is also equal to 1 over 2 pi FC. So, what is impedance? The impedance is the joint effect of the resistance and the reactance. So, when we talk about the impedance, this is the sum of the effects of the resistance and reactance. So, number 3, RLs and C in the circuit. So, what is the behavior of these three elements in a given circuit? So, for resistance, it takes the current that is in phase with the voltage across it. Let's say, this is your sinusoidal wave function. For the voltage, the current is also in the same phase with the sinusoidal wave of the voltage. So, for the inductor, it takes a current that lags the voltage across it by 90 degrees. So, let's say you have a sinusoidal wave function of the voltage. You have a current that lags by 90 degrees. So, the current function or the current waveform lags by 90 degrees, or it is behind by 90 degrees. So, for capacitor, takes the capacitor takes current that leads the voltage across it by 90 degrees. So, for inductor, it is lagging. For a capacitor, it is leading. So, when you have a voltage of sinusoidal wave function like this, you will have a current that leads the voltage by 90 degrees. So, this is the behavior of these three elements in a circuit. So, for number 4, we have the complex equivalent of impedance. So, take note that this Z is a vector quantity. So, R is equal to J times XL minus XC. So, this is in terms of ohms. So, if you wish to get the magnitude of Z, or the magnitude of your impedance, this is just equal to square root of R squared plus XL minus XC squared. So, if you want to get the angle of this Z, this is R tan of XL minus XC over R. So, take note that this angle will be negative if your capacitive reactance is greater than the inductive reactance. This will be positive if the inductive is greater than the capacitive reactance. So, number 5, we have the AC powers. So, referring to this power triangle, so your P is the active power, or also called the true power. So, that is equal to I squared R, or EI cosine theta. Take note that these P's here are magnitude values. So EI cosine of theta. So, the unit of active power, the unit is watts for active power. That is W. So, you have reactive power Q. So, this is the power as the influence of your capacitor and your reactor. Capacitor and your inductor. So, your Q is equal to I squared X, or the reactance, or equal to Q equals EI sin theta. So, the unit is VARS. So apparent power S, that is S equals TI. So your S squared is equal to P squared plus Q squared, referring to this power triangle. So for the power factor, this is the ratio of your true power to apparent power, which is equal to P over S, or cosine of theta. So your cosine of theta is also equal to R over C. So note that for a lagging power factor, for inductive, that is for inductive. So inductive loads will have a lagging power factor. So for capacitive, that will be a leading power factor. So for lagging power factor, that means that your voltage is leading the current, or the current is lagging the voltage for that specific circuit. So for unity power factor, that is for resistive load. So for unity power factor, this means that the voltage and the current are in phase. So when we say in phase, there is no angle difference, or there is no phase difference between the waveform of the current and the voltage. So for zero power factor, that is a reactive load. So there will be no resistance. So let's say, for example, you're given of E equals Em sine omega t plus alpha and I equals Im sine omega t plus beta. So the power of this system will be equal to Im over 2 cosine alpha minus beta.
A 240 volt, 25 Hz sinusoidal generator is connected to a 20 ohms resistor. Determine the instantaneous current when elapsed time is 0.01 second. A 15.43 amperes, B 16.3 amperes, D 16.97 amperes, D 12.0 amperes.
For this problem, we are asked to find the instantaneous current given a 240 volt 25 hertz sinusoidal generator. So first, we're going to get the maximum current to find the function of the instantaneous current. So the instantaneous current I of t is equal to sine omega t. So we have to find this Im. So given a 240 volt, we know that the 240 volt, take note that if it is a given 240 volt 25 hertz, that 240 volt is an RMS value. So since you're given an RMS, and we know that Im is equal to Em o E maximum over R, and your the maximum voltage is just equal to square root of 2 times the ARMS. So applying the formula, you get square root of 2 times 240 over 20. So you will get 16.97 amperes. So that is your maximum value of your current. Now we're asked to find the instantaneous current at 0.01. So we know that I of t is equal to Im sine omega t. Then therefore, this is 16.97 sine omega t is this 2 pi f. Omega is 2 pi. So 2 pi f. So 25. So 25 hertz times the time. So this is I of t is equal to 16.97 sine 50 pi t. And therefore, you will get I of 0.01, that is 16.97 amperes.
A varying current with a periodic waveform flows through a 10 ohms resistor, such that for the first 6 seconds, it is constant at 10 amperes. For the next 4 seconds, it is 0, and for the next 2 seconds, it is constant at 1 ampere in the reverse direction. Determine the average and RMS values of this current in amperes. A 4.83 and 7.08, B 5.83 and 8.21, C 4.83 and 8.21, D 5.83 and 7.08.
For this problem, we are given a varying current. So, as shown, so we have for the first 6 seconds, you have 10 amperes. For the next 4 seconds, you have 0 amperes. And then for the next 2 seconds, you have a value of 1 ampere but in the negative or the reverse direction. So, we're asked to find the average and the RMS values of the current. So, in order to find the average value, so the average value of the current is equal to 1 over the period integral of I of t dt from 0 to t. So what does this integral mean? So this is the area of the curve from 0 to t. So your t is your period. So this is one cycle. So 12 seconds. So applying the formula, you will have 1 over 12. So integral of I of t dt from 0 to t is equal to 10 times 6 plus 0 times 4 plus negative 1 times 2. And that will be equal to 4.83 amperes. So, in order to find the RMS value of the current, that is the square root of 1 over t integral from 0 to t of I of t squared dt. So, that will be square root of 1 over 12 multiplied by 10 squared times 6 plus 0 squared times 4 plus negative 1 squared times 2. And that is 7.08 amperes.
Three loads units A, B, and C are connected in parallel and take current that are 12, 10, and 15 amperes respectively. Assuming IA to be the reference phasor, IB leads IA by 30 degrees and IC lags behind IA by 65. Calculate the total resultant current. A 28.33, B 30.21, C 26.46, D 32.10 amperes.
For this problem, we're asked to find the total or the resultant current. So, having A as our reference. So, as shown, so it says in the problem that you have IB that leads IA by 30 degrees and IC that lags IA by 65 degrees. So, the total current will be equal to 12 bar angle of 0 degrees, so plus 10 angle of 30 degrees, plus 15 angle of negative 65 degrees. So, inputting this in your ES calculator by ES, you have the mode complex. So, you will get 28.33 amperes.
An industrial coil has a resistance of 32 ohms and a reactance of 24 ohms and rated 440 volts at 60 Hz. A factory will connect the coil to a 440 volt 50 Hz supply. Solve for the value of a series resistor needed to avoid overcurrent condition. A 2.07 ohms, B 2.64 ohms, C 2.44 ohms, D 2.25 ohms.
So for this problem, we are given an industrial coil so of resistance 32 ohms and reactance of 24 ohms. So rated at 440 volts 60 Hz. So this will then be connected to a 440 volt 50 Hz. So therefore, there must be something that we add onto the system to avoid overcurrent. So to avoid overcurrent, this means that the impedance at 60 Hz must be equal to the impedance at 50 Hz. So therefore, a resistor is needed to be connected to the system, so we avoid overcurrent condition. So at 60 Hz, you have 32 squared plus 24 squared. This is your impedance. So For at 50 Hz, the impedance is R plus 32. So R in series with the 32 ohm resistor plus this is the new reactance. So this is 24 multiplied by 50 over 60 Hz. So that is squared. So you will have 1/6 equals R plus 32 squared plus 400. So you will have R squared plus 64R minus 176. So by your ES, by your calculator, so you have mode 53. Mode 53, you will have 2.64 ohms.
An inductive coil takes a current of 2 amperes and consumes 160 watts when connected to a 240-volt AC supply. A second coil, when connected across the same supply, takes 3 amperes, 500 watts. Mali.
For this problem, we have two inductive coils. So one is taking 2 amperes and 160 watts when connected to a 240 volt AC source. The second one is if connected to the same supply, you have 3 amperes and 500 watts. So we will be able to get the impedance if we divide the supply voltage to the current drawn. That is 120 ohms for Z1. And we know that R1 is equal to 160 watts over 2 amperes squared. That is P over I squared to get the R. So you will have 40 ohms. So your impedance is 120, your resistance is 40. So you will have Z1 which is 40 plus this is 120 squared minus 40 squared. The square root of that is 80 square root of 2. So you will get the reactance. So for Z2, same thing. You divide 240 volts by a 3 ampere drawn. So you will have 80 ohms. And then you will have the R2 from the power. So I squared R. So that is P over I squared. So 500 over 3. That is 55.56. So you will have a Z2 of 55.56 plus J 57.56. So in series, the Z total is Z1 plus Z2. So you will have 95.56 plus J1 70.7 or 195.63 angle of 60.76 degrees ohms. So the current is, you just divide the supply voltage by the total impedance. So 240 over 195.63, you will have 1.227 as your current. So we know that the power is equal to I squared multiplied by R. So that is 1.227 plus the total resistance is 95.56. So you will have 143.87 watts as your final answer. So since the choices in the given is the nearest is 144.56, so you have to choose letter A. So but it's just a matter of very small quantity because of maybe it's because of rounding off, etc. So since the difference between those in the choices are very significant naman, so you choose letter A as your final answer.
A 1/2 HP 110 volt 60 Hz single-phase induction motor has an efficiency of 88% and a power factor of 0.707 lagging at rated load. This motor is to be connected temporarily on a 220 volt 60 Hz line. Determine the resistance required to be placed in series with the motor in order to prevent the machine from experiencing overcurrent. A. 25.2 ohms, B. 23.5 ohms, C. 19.5 ohms, or D. 27.6 ohms.
For this problem, we are given a single-phase induction motor of 0.5 HP rating or 1/2 HP rating. So with 110 volts as and 60 Hz as also the voltage and frequency rating. So the efficiency is 88% and the power factor is 0.707 lagging. So it is so we can already find the the current, so the line current I. So that is power input or P out over the efficiency divided by the power factor and divided by E. So that will be 5.45 amperes. So we can also get the theta. So that will be arc cosine of your power factor. So which is 45 degrees. And also, if we have like 5.45 amperes, we can get the impedance. That is E over I, which is 110 over 5.45. So you will have 20.183 ohms. So, or Z equals 14.27 plus J 14.27. Since this one is obtained from uh, 20.183 angle of 45 degrees. So, yan. So, it is said that it is connected to 220 volt 60 hertz. So, you will have, let's check the impedance. So, the impedance at needed to prevent the machine from overcurrent is 220 over the same current, which is 5.45. So that is 220 or 5.45. This will give us 40.367 ohms. So since we need a resistor to be connected in series, so that will be 14.27 plus R. So the impedance is 40.367 squared multiplied equals to 14.27 plus R squared plus 14.27 squared. So you have R as your unknown, your by ES calculator. Just replace this by X, so you will have shift solve. So your R is equal to 23.5 ohms.
A series resistance capacitance or RC circuit is connected to a 230 volt 60 cycle source. If the power taken by the circuit is 4,800 watts and the voltage drop across the resistor is 115 volts, calculate the capacitance of the capacitor. A 540 microfarad, B 530 microfarad, C 556 microfarad, D 503 microfarad.
So for this problem, we are given series resistance capacitance or RC circuit. So we have 4,800 watts as the power across the RC series circuit. So we know that the resistance is equal to the voltage across the resistor over the power. So that will be 115 squared over 48. You will have 2.755 as your resistance. Now we know also that P equals I squared R, or your current, the magnitude of the current, is equal to the square root of P over R, and that is 48 over 2755, and that we will have 41.74 amperes as your current. So your theta, or your power angle of power factor, so we have cosine of P over EI, so that is power over the apparent power. So you have 48 over the true power, the apparent power of 41.74 times 115. So you will have 60 degrees as your theta. Now we know that that tangent of theta is equal to xc over r. So you will have xc equals arctan of theta. So you will have 4.77 ohms as your value of the xc, or the capacitive reactance. So in order to find the C, or the capacitor value, or capacitance, so the reactance is equal to 1 over 2 pi fc. So you have your capacitance equals 1 over 2 pi f xc. So your value of the capacitance is equal to 556.096 microfarad.
A 50 and 100 microfarad capacitors are connected in series and across a 100 sine omega t plus 30 degrees voltage. Write the equation of the current. A 1.26 sine omega t plus 120 degrees, B 1.26 sine omega t plus 90 degrees, C 5.65 sine omega t plus 120 degrees, D 5.56 sine omega t plus 90 degrees.
So for this problem, we're given two capacitors, values of 50 and 100 microfarad, so connected in series. So we got to find the total capacitance first. So you have 33.33 microfarad as your total capacitance. Now we obtain X sub C, which is from 1 over 2 pi FC. You will have 79.58 ohms as your reactance. Since you will have you don't have resistance, your XC is equal to your impedance. So your XC for this condition is equal to your impedance. So we know that I is equal to E over C. So this is vector. So you have, this is 100 angle 30 degrees. This is from the sinusoidal function 100 sine omega t plus 30 degrees. You can rewrite that as 100 angle 30 degrees. So this 79.58, since you have a capacitive reactance, that is negative J 79.58 or angle of negative 90 degrees. So that will be equal to 1.26 angle of 120 degrees. So this is your I of t. So your I of t is equal to 1.26 sine omega t plus this angle, theta, 120 degrees.
A series circuit consisting of a variable resistor in series with a capacitance of 80 microfarad is connected across a 120 volt 50 Hz supply. To what value should R is adjusted so that the power absorbed by the series circuit will be 100 watts? A 20 ohms, B 18 ohms, C 15 ohms, or D 12 ohms?
For this problem, we are given an 80 microfarad capacitor connected across 120 volt 50 hertz source. So we're asked to find the value of the adjustable or the variable resistor R, in which our power is 100 watts. So first we get the XC or the capacitive reactance. So that is 1 over 2 pi FC, though that will be 1 over 314 times 80 microfarad. So you will have 39.81 ohms as your XC. So we know that your Z is equal to R plus J times, or this is R minus J plus 39.81. So your Z is equal to R squared plus 39.81 squared. So now, we know that the current is equal to the voltage over the impedance. So this one is by magnitude. So you will have 120 over R squared, square root of R squared plus 39.81 squared. And we know that the power is equal to I squared times R. So this one is your I squared times R, which will be equal to 100. So this one, you manipulate, you will get 14,400 R plus 100 R squared plus 39.81 squared multiplied by 100. So you will have this quadratic function or quadratic equation. So by your ES, that is again mode 5.3. Mode 5.3. So this one is A, B, and C. So you input this in your calculator, you will have two positive values. So this value 12 ohms is less than the other value. We're asked to find the minimum value. So your answer will be 12 ohms.
Capacitor is rated 100 kVAR, 380 volts, 50 Hz. What will be the rating at 60 Hz, 220 volts? A 50 kVAR, B 40 kVAR, C 90.9 kVAR, D 57.7 kVAR.
For this problem, we are given a capacitor rated 100 kVAR at 380 volts 50 Hz, and we're asked to find the rating at 60 Hz 220 volts. So we know that our Q or the kVAR, the reactive power is equal to EC squared over XC, and that is EC squared over 1 over 2 pi FC, which will give EC squared 2 pi FC. And from this, we know that the reactive power is directly proportional to the square of the voltage across the capacitor times the frequency. So you will have a relationship of Q2 and Q1, which is EC2 squared F2 over EC1 squared F1. So therefore your Q2 is equal to Q1 multiplied by EC2 squared F2 over EC1 squared F1. So substituting all the values, you will have 40.22 kVAR.
A resistor and a capacitor are connected in series across a supply of 250 volts. When the supply frequency is 50 Hz, the current in the circuit is 5 amperes. When the supply frequency is 60 Hz, the current is 5.8 amperes. Find the value of the capacitance. A 58.3 microfarad, B 60.2 microfarad, C 69.1 microfarad, D 70.2 microfarad.
For this problem, we are given an RC circuit. So at 50 Hz, so you have 250 volt as source. The current drawn is 5 amperes. And at 60 Hz, the current drawn is 5.8 amperes. So we know that your impedance is equal to the voltage over the current. So you will have 50 ohms as your impedance at 50 Hz and 43.1 ohms as your impedance at 60 Hz. Now, knowing the equation for impedance, which is Z squared equals R squared plus C squared, where your XC squared, so where your XC is equal to 1 over 2 pi F times C. So your 2 pi F is 314 times your capacitance at 50 Hz. So at 60 Hz, that is 377 C. So you have equation 1 and equation 2. So subtracting equation 2 from equation 1, we obtain 50 squared minus 43.1 squared is equal to 1 over 314C squared minus 1 over 377C squared. So manipulating, multiplying both sides by 314 squared, 377 squared times C squared. So you will have this equation. So solving for C, you will have 69.5 microfarad.
A 2 HP 230 volt single-phase induction motor draws 12 amperes at full load efficiency of 75%. It is desired to increase its power factor to 0.85. Determine the capacitor K-bar needed to achieve such purpose. A 0.78, B 0.68, C 0.88, D 0.58.
For this problem, we're given a 2 HP 230 volt single phase induction motor. So that draws 12 ampere at full load. So the efficiency is 0.75. So in order to get the input power, that is P out over the efficiency, which is equal to 2 HP over 0.75. And we convert HP to watts, we have 1989.33 watts. So we know that our apparent power, or your S, is equal to E times I. That is 230 times 12. So you have 2760 VA, or volt ampere. So your Q is equal to square root of S squared minus P squared. And that will be square root of 2760 squared, this one, minus 1989.33 squared. So you will have your Q, which is 1913 vars. Take note that this vars is inductive vars. So at power factor equals 0.85, your theta is equal to, it is desired to increase the power factor to 0.85. So your theta is equal to R cosine of 0.85. The new theta will be equal to 31.788. So we know that the tangent theta is equal to Q over R. So this Q, the resulting Q, is equal to Q inductive minus Q capacitive. So we're looking for the capacitive Q. So we have Q inductor minus R tan theta. So that will be 1913 minus 1989.33 tangent of 31.788. you will have 680 vars or 0.68 kvar as your final answer.